All right. Well, our next speaker is Rahul Singh from Northeastern University, and he has a slight title change. We're now talking conormal varieties and orbital varieties.
Thank you, Paul. And I do want to mention that there's a slight title change, but it's basically the same object. The conormal varieties I'm going to be talking about are, at least from the flavor of questions that I'm answering, basically exactly what Spaltenstein varieties are. If you already know, and if not, maybe after the talk, I can tell you why it's exactly the same thing. So I'm not cheating you out of the topic. Okay, so let's just do some setup. And okay, I'll work over complex numbers, but really it works for very good characteristics or large primes if you want. So I have this semi-simple algebraic group and a Borel subgroup and parabolic subgroup containing V. So this will give you a hint that I'm going to be talking about Schubert varieties where, let's just say if it's on this page. The Schubert variety is going to have dimension equal to the length of W. Okay, so I'm going to study this compact homogeneous space G mod P, and we have the cotangent bundle which we can define right here. So let's just do a couple of examples. So this is maybe the most classical one, or maybe the second most classical one. You start with this simple linear group, and you take your parabolic to be exactly your Borel, so you have this upper triangular matrices in G. And then your homogeneous space, this X is just the flat variety. And another example of this group SP4. And I take this parabolic group to be, well, you can see from the picture that I basically want a 0 in the bottom left 2 by 2 corner, and the rest is varying freely as long as it is in SP4. So this I can identify actually with Lagrangian subspaces of a 4-dimensional vector space. So I have C4 and I set up a symplectic form on that. And then I ask what are the Lagrangian subspaces of that. Okay. So a little bit more notation. Torus, normalizer, root systems, simple roots, wide group. I mean, it's pretty standard for this audience. Okay, so for me, a Schubert variety is a B-orbit closure in X. And I'm going to get Schubert varieties of this form. This XW, which is the closure of BWP. So of course, since I have not said anything about what this parabolic is, the Schubert varieties will be indexed only by these minimal representatives with respect to P. You won't be getting all the while group elements. And I do want to, I already talked about this, but this is my notation, which has not always been the notation this week. Okay, so what's the meat? I want to talk about this conormal variety of a Schubert variety. So talk about that first, I want to define it. So if I was dealing with a smooth subvariety, if XW had been smooth, things would be easy. I can just go back to my differential geometry class and I can define a conormal bundle. Because at any smooth point, I have a manifold and a submanifold. So I have a tangent space and a tangent subspace. So the subspace has an annihilator which lives in the dual space. So the annihilator lives in the cotangent space at that point. So I define a vector bundle by just taking that subspace. So I get a vector subbundle of the cotangent bundle. So here I do basically the same thing, but what I do is I first look at the Schubert cell, which is part of the smooth locus. And more generally, I would just have a subvariety, and I just look at the smooth locus, and I define the conormal bundle there. And then I take the closure inside T star X. So I do want to say that with this kind of definition, you want to sort of assume that the thing you started with was closed to begin with. Otherwise, once you take closure, you have to restrict again to where you were looking. And the other objects in my title, orbital varieties. So I'll just give you like a working definition, one that's sort of enough to get us started. So I have this unipotent radical of the Lie algebra of the Borel. So when I'm dealing with SLN, it's just like these strictly upper triangular matrices. And I take a nilpotent orbit closure. So if without the lambda, I have n, which is just the variety of nilpotent matrices in G. And I look at the orbit for the action of the group by conjugation or by the adjoint action. And I take orbit closures. So I have this setup. And what I do is I intersect it. And when I intersect it, I get a variety with many irreducible components. So each of those components I'm going to call an orbital variety. So these are going to be affine, these are closed subvarieties of U, which is itself just a vector space, just the strictly upper triangular matrices. And the reason these two go together in this talk is coming up right here. So I start with any compact homogeneous space X, so any choice of P. I have a Springer map. So I haven't really talked about the structure of what this T star X looks like beyond saying, of course, it's well defined, it exists. And I'm not going to, because without talking about that, I can't really describe this Springer map in detail. But I think I'll just skip that, and I'll say that the working proposition, the one that's really important for me, is that under the Springer map, the image of any conormal variety is an orbital variety. And this sort of goes the other way too, actually. You start with an orbital variety, you'll always be able to find a conormal variety such that the orbital variety can be recognized as the image under the Springer map. And in fact, actually, you can just restrict yourself to looking at Schubert varieties in the full flat variety, and that's fine. You'll still get all the orbital varieties. But it's nice, this way you get, the same orbital variety you can study from as the image of a conormal variety coming from some different compact space, and sometimes it helps, which it is going to today, because I'll talk about the Grassmannian soon. Okay, so just to give you an idea of the flavor of the problems that I am sort of studying, which is the maybe less popular flavor when you're looking at these conormal varieties. A lot of people want to study this cohomology and the associated representation theory that comes out of it. So what I'm studying is really the local geometry of these conormal varieties. So here's one of the motivating problems is if I know the fiber of the conormal, so this conormal variety really it's defined locally, right? At each point you just talk about what the behavior is at that point locally. And to what extent can I recover the singularity from the fiber at that point? And in general, it's you can't always, is quite clear, although maybe for Schubert varieties you can. So one example, which I don't have in this picture, but I want to talk about, if you look at this curve, y square equal to x cube as a curve sitting inside C2, and you have the singular point at 0. When you draw the conormal variety, you'll get basically just a vector bundle. And even at the point, the singular point, you're not able to capture that singularity just by looking at the conormal variety. So, this conormal variety is lossy. You lose some info. So this is the next problem, pretty much in the same flavor. I want to understand this local geometry. So I want to do it the hard-working way, or the classical way of write down the equations, do some Grobner geometry, see where you can go. So this is the one I'm really going to tackle today. But this is sort of related. If you have a resolution of singularities, then you can actually start trying to do some of this cohomology business. And this is like, every time I say local geometry, I want to ask, is it normal, is it Cohen-Macaulay? The question asks itself even if you never know the answer. Okay, so here I'm going to give you a first class of solutions. It's not very, the answers are nice, but they apply very restrictively. So if I have a divisor, so I have a codimension 1 Schubert variety, and I want to talk about the conormal variety of that. So here's a theorem that if you look at that, you can basically compactify it into an affine type Schubert variety. So I have this technical condition, which is that alpha is a long simple root. But outside, let's just for a minute look outside type B and see. So I don't have a problem with long and short. How this proof sort of goes is you have the fiber which lives in the nilpotent cone, and you compactify it by saying x goes to xt inverse x, which is sort of actually, and let me see if I have more. So maybe I'll just, as a motivation or intuition, Lustig gave a compactification of this nilpotent cone in type A as an affine type Schubert variety. And he identified that all these nilpotent orbit closures become G-stable Schubert varieties in the affine Grassmannian. And we looked at that map, and that map is very special and doesn't really work outside type A. But if you start with a nilpotent matrix X such that X square is 0, which is very restrictive, then you can just define the map just makes sense anyway. And you start with that map, and then you chase arrows, and you do a bit of Schubert calculus. I mean, you do some combinatorics on wild group elements, and this thing sort of falls out. The point is that when you're studying this conormal variety, the generic points are easy to write down because the generic points you have a smooth vector bundle, you have vector bundle on a smooth sub variety. So if you have a map somehow into a compact space, you just need to show that it's birational, and then you have nice results about its closure. So well, okay, now that I have this result, I have all the questions I was asking, half of them are sort of immediate. And this has been a sort of, I mean, this kind of technique, this is embedding and compactification, I'll talk about again in the next couple of slides, and gives strong results but when it works, but it doesn't work very often. And it's reasonable that it doesn't work very often because the conormal varieties are in general much more complicated than Schubert varieties. Okay, so just as an aside, because now I'm going to make some technical restrictions on the next half of the talk. So simple root is called co-minuscule if the coefficient of alpha in the highest root is 1. And I'll just draw you all the ones. So these are all the finite type Dynkin diagrams that admit co-minuscule roots. And the ones I dotted out are exactly the ones which are co-minuscule. So in type A, all of the roots are co-minuscule, but otherwise you hardly ever get anything. Okay. And then I'll look at these maximal parabolic subgroups. So when I talk about a maximal parabolic subgroup, I remove one root. And I insist that the root I'm removing is a co-minuscule root. So one of the ones I marked in the last diagram. And I'll study now just that compact space and conormal varieties there. So when I look at a Schubert variety inside X now I'm looking at a Schubert variety inside the co-minuscule Grassmannian. I construct this, well, I have this conormal variety, but when I just look at the conormal bundle on the smooth part, the fiber has a nice B action, and I can really, well, the fiber is B stable. So this UW that I have here, it's the set of roots. So it's the subspace of the upper triangular matrices, which is supported on the roots which are positive under W. And they have to begin with, they have to be in the unipotent radical of the parabolic. So these two conditions tell you that with a little bit of combinatorics on this Y group elements, you see that you get a B stable object. And that's very special to co-minuscule types. Outside that, you basically never get it except in like very trivial cases, or when your Schubert variety that you're studying is already kind of smooth, so you're not interested so much in the conormal variety. So there's a big restriction to where this theorem can be generalized. But the theorem is very nice that once you have this B stable fiber, you can construct, so this Bott-Samuelson variety which is resolving W, I have this B quotient on the end, and I can just work around that and I can construct a vector bundle on that Bott-Samuelson with the fiber being UW. And once you have this, you see that the map is proper and birational. Is quite easy to show. The challenge all along was constructing this object, or really being lucky that this object exists. And you'll see I also made another one here. This is resolving the image of the conormal variety, which in this case is the orbital variety. So this is also a resolution of singularities for the orbital variety, except for I mean it is, and the only part I've not told you is that the map mu was actually proper birational from here. So in general it won't be, but from the co-minuscule Grassmannian you'll always get a proper birational map. Otherwise you have to see sort of when it is and when it is not. So yeah, okay, so now I have some resolutions. The next thing I want to talk about are, okay, there's one more thing. So I talked a little bit earlier about this compactification for the conormal variety of the divisor, and I want to see how far I can take it. So maybe here. So Lakshmibai, who's my advisor, and William Slofstra and Ravi Kumar, they started with just Lustig's compactification of the nilpotent cone, and they said, well, the cotangent bundle resolves certain orbits. Can I sort of compactify this cotangent bundle so it's again a Schubert variety of an affine Schubert variety? And generally it doesn't work, but it works when X is a co-minuscule Grassmannian. And once again, really what's happening is that when you look at the matrix, in T, the nilpotent matrix that shows up in T star x, or the orbit that is being resolved by T star x, that x satisfies x square equal to 0. And that really allows all of this to go through.
So, to be clear, this top theorem, we say Lustig's version was x is.
No, Lustig's version was n.
Type Lustig's version x is not co-minuscule, but it's type A?
Yes.
Okay.
Yes. And there, I mean, all of the n, not just the ones that come from co-minuscule orbits.
Right.
Although there is a version by Achar, Henderson, Rishi, which says that if you have the nilpotent cone, you have sort of a 2-to-1 map from a small Schubert variety in an affine Grassmannian. And that works everywhere. And they sort of figure out where the map is 1-to-1 and where it's 2-to-1. But it's only an isomorphism of points. And it's an isomorphism of varieties when they already know normality. So, yeah. Oh, I didn't see you. Anyway, so I started with this embedding and asked the question, and sort of this was the motivating part to begin with. Like, okay, you compactify the cotangent, but it's nice, it's not so great because, I mean, the cotangent bundle is very nice to begin with. The idea was you have this conormal variety sitting inside their half dimension, and maybe you compactify it and you again get a Schubert variety, and then you have something strong. And it doesn't work very often, but it works when the opposite Schubert variety is smooth. I know this looks sort of like a geometric condition, but really is a combinatorial condition on W. In the sense that when you chase the proof, you realize that in a co-minuscule Grassmannian, smoothness is equal to homogeneity, which means that there are very few of them. And then it's really just combinatorics on the W. Okay. So as an example, you can take when the case of a determinantal variety or a skew-symmetric determinantal variety. And all of these were classically identified as open cells in certain co-minuscule Grassmannians by Lakshmibai and Seshadri in the 70s. And in all of these cases, this result applies. So I get all these nice geometric results about the conormal variety of a determinantal variety. I think all of these, certainly without the symmetric, skew-symmetric thing, this was done by Strickland also quite a while ago. I'm not sure if anyone wrote a symmetric or skew-symmetric version of that. But this is a different proof because Strickland's proof was very much Grosvenor basis-based, doing a lot of calculations and actually showing that the ring of coordinate the coordinate ring is normal, sort of inductively. Okay, so once I have a Schubert variety, I have all the nice answers I want. Okay, so now I'll put up a conjecture here, but this conjecture came after the theorem that's hidden as a punchline. So I have this Springer map, and I have this structure map just defining the cotangent bundle. So it's clear. So the equation, the conjecture says that the conormal variety set theoretically, or I mean it's a conjecture, so I can question is it scheme theoretically also equal to this intersection. So I mean one side is clear that the left hand side has to be contained in the right hand side, just because the conormal variety lives over XW and has to be in the pre-image of its image under mu. And okay, so the main result is, well actually, this conjecture, when the opposite variety is smooth, it sort of follows from the embedding I was talking about with Ravi Kumar's Lofstra. Because what happens there is that both these maps, phi and mu, sort of become projections in affine type flat varieties. And then this statement becomes a question of, is a Schubert variety equal to the intersection of the pre-images of the Schubert varieties that go down in the projection? And that is true, and that is true in a scheme theoretic sense. But more generally, this holds set theoretically in all the classical types. And the proof is, again sort of in a ugly way well, not an ugly way, but a classical way of looking at these co-minuscule Grassmannians as precisely the Lagrangian Grassmannian or orthogonal Grassmannian, and doing it in that setting rather than in a type independent setting. So, I mean, the conjecture is not quite enough to say I have equations describing the conormal variety. It's just saying that if this conjecture were true, writing the equations up to reducedness is the same thing as writing equations for the associated orbital variety, which is the image under mu. And here I'm going to give you these equations for this orbital varieties. They look like this. So I'm going to have some integers rij, which really depends on the combinatorics of the word w. And then I have this condition that the matrix has to be x square equal to 0. And there are rank bounds on the bottom left corner for every possible ij. So if you've seen this, I mean, this is basically a matrix Schubert variety along with an extra condition that the matrix has x square equal to 0. And the proof really goes by understanding the resolution that we had. Because the resolution has a description as a closed subvariety by equations, and it's mapping properly to what we want, which is the closure of something, which is kind of hard to figure out. So what we say is, suppose something satisfies these equations, basically find that you can lift that point to something in the resolution, and therefore it satisfies, therefore it was in the conormal variety to begin with. So with that I'll end. I think 30 seconds.
Questions?
In any of these Frobenius split spaces you're running into, do you know what, how much can you say about what are the compatibly split subvarieties?
I mean, everywhere I'm getting Frobenius splitting is by identifying it as a Schubert variety. So then the ones that I know are compatibly split are just the, yes, but I mean, I haven't identified any of them as being interesting from this point of view. Except, let me go back to this one where it does help. This one. So when I'm dealing with the co-minuscule one, the compactification is, I mean, to begin with, the cotangent bundle itself is compactified. So all the conormal varieties are compatibly split in this case. Not in the case where there was the divisor, because there each conormal variety is compactified as a Schubert variety, but the cotangent bundle is not. So they're not compatibly split. But in this case, all the ones that come from the opposite being smooth, the conormal variety is, I mean, compatibly split. So, I mean, it's weak because there's not so many of them where the opposite is smooth. But, I mean, you have what you have.
Okay, let's thank Rahul again.